We live in a time of extraordinary discovery for astronomy and astrophysics. The next decade will transform our understanding of the universe and humanity's place within it. Every decade, agencies that provide funding request a survey to assess opportunities to forward our understanding of the cosmos. The survey identified that investigating Earth-like exoplanets was one of the three important topics to look at this decade. With more than 5,000 exoplanets discovered and 59 of these being possibly habitable, it begs the question of how we're going to find these habitable planets. And the answer lies with NASA's new flagship mission, the Habitable World Observatory. Slated to launch in the late 2030s to early 2040s, this mission is building upon the framework of two other mission concepts: the Large Ultraviolet Optical Infrared Surveyor and the Habitable Exoplanet Observatory. HWO would be used to locate other habitable planets around other stars, closely examining their atmosphere to see if life could be present. It would do this by blocking light from these stars, which will allow fainter light reflecting off an exoplanet to be seen. Chemical elements and compounds absorb and emit light at unique wavelength compositions, meaning light exposed to a planet's atmosphere creates the looking glass into its makeup. Scientists will then take these light signatures and use a process called spectroscopy to break down this composition. Spectroscopy involves the splitting of light, or more precisely electromagnetic radiation, into its constituent wavelengths, which is done in the same way as a prism splits light into a rainbow of colours. It uses what is known as diffraction grating to disperse the light, which is projected into charge-coupled devices similar to those used in digital cameras. The 2D spectra are easily extracted from this digital format and manipulated to produce 1D spectra, which contains an impressive amount of information. But how will the HWO block this starlight? There is two ways that this could be achieved. It could utilize a large external sunshade which would unfurl from the HWO after its launch into a massive sunflower-shaped umbrella. Alternatively, it could use an internal starshade known as a coronagraph, which was used to observe the sun's corona, hence the name. NASA has decided to focus on coronagraph technology, used on several other telescopes such as the James Webb Space Telescope and the Nancy Grace Roman Telescope. The WM Keck Observatory is already using such technology to picture thermal emissions from young and hot gas giant planets. Earth-like planets the HWO will set its sights on can emit light 10 billion times fainter than that of stars, meaning this technology will need to push starlight well beyond its current limits. An idea introduced at a Caltech meeting to enhance the suppression of light for the coronagraph was to put a mirror within it that can be deformed to control light rays. Employing thousands of actuators to drive the shape of the mirror, as well as push and pull on its reflective surface, could stop stray light from making it into the final image. A similar idea is being enacted for the Nancy Grace Roman Telescope, which will allow astronomers to see gas giants around 1 billion times lighter than that of their parent star, though they will need to suppress starlight to another factor of 100 than what is set to be put into Roman's build. Astronomers are also at work selecting Earth-like targets for the future telescope to gaze upon. The hunt will include the Keck Planet Finder, which has been specifically designed to look for Earth-like planets on small red stars. This is the exciting future of finding possibly habitable planets within our universe. The video playing right now is a simulated observation of our solar system through the eyes of the HWO, viewed from a distance of 40,000 light years away, which is an exciting testament to what this future telescope will be able to achieve.